It's obvious that the world is shifting away from fossil fuels and toward renewable energy sources. Wind and solar farms are everywhere. But 70% of our planet is covered in oceans that harbor an immense amount of energy in the form of waves. This has led to a variety of wave energy converter devices. A lot of research needs to be done to find the best method to exploit this potential, with just a few of many ideas shown here. To enable some of this research to be done at MTU, Team 63 was tasked with developing a point absorber wave energy converter with attributes conducive to testing and research, such as modularity and wireless capability. Point absorber wave energy converters work by harvesting the energy that can be generated by the relative motion between a buoy body that oscillates up and down and a drag plate body that remains essentially fixed. The energy can be captured through a variety of methods. Our team chose a linear motor that had the stationary portion of the motor mounted to the aluminum and polycarbonate drag plate subassembly, and the moving portion of the motor attached to a 3D printed buoy. The two bodies were linked together using a linear guide system to prevent the transmission of the lateral forces on the buoy to the motor shaft that connects the bodies. The linear guide system consists of two linear guide rails fixed at each end by rigid brackets and two linear bearings that are bolted to the drag plate subassembly. The positions of the guides can be easily adjusted due to the use of shaft collars in our design. Combining these bodies and the linear guide system creates smooth and aligned relative motion between the two bodies that can produce energy through the linear motor. With the motor and a few other components assembled through non-permanent connections, a fully functional and modular prototype is created. The output of the motor is measured by using a microcontroller, a BeagleBone Blue, to read the voltage produced and wirelessly transmit this reading to a computer where the data can be recorded and analyzed. From this project, we were able to prove that rapid prototyping of custom buoy shapes was a viable method of creating a completely modular point absorber wave energy converter. Moving forward, the buoy shape used in this device could be optimized through the same 3D printing method that was used for ours. In addition, the onboard controller could be used for feedback control and operation in an array of wave energy converters. All of these potential steps could lead to harnessing more energy from the waves than our current prototype.